Hello ATS 114 students, Dr. John Schrage here, and I am here to walk you through a little bit of Lab 2 from your manual. This is about Earth-Sun geometry. Now if you're in ATS 113 or EVS 113 right now in the class, you already have learned quite a bit about how the angle of the sun is going to be determining a large part of how much heating from the sun there will be on any given day. So we don't really need to review that frankly kind of basic concept a little bit, but I know that students get into a little bit of trouble in this lab with regard to the following all the directions carefully enough for their diagrams that they're producing to be useful. In general, this lab is pretty straightforward as long as you read through the text and then just follow the instructions very, very carefully. You'll have no problems getting through all the little intricacies of the math and stuff like that. And your TAs can help you with stuff like that. But I do want to spend a little bit of time on two of the different kinds of diagrams that you're going to be doing this in this lab. One set of the lab activities has a diagram that looks something like this. And what the diagram is saying here, if I zoom in a little bit, is that the Earth-Sun orientation changes throughout the year as the Earth revolves around the Sun. Using figures 2.3 and 2.4 as models, sketch two similar diagrams for each date given below. Now, it actually says here first draw the Earth's axis and then the equator and then all four locations on this sunny side of the globe. And I know, I've done this lab many, many times, I know students often don't read those instructions carefully enough and or don't quite make sense of what's going on here. So let me make it a little clear here. This is figure 2.3 and that's figure 2.4. Those are the figures that you're trying to reproduce on your diagrams there in your workbook. So let's focus first on that 2.3. You have a little globe there. That circle is supposed to be a globe, just like the globe that they have drawn over there on the left in their figure 2.3. And I'm going to give you a little hint. They don't tell you to do this, but go ahead, take a look, see you got those three rays of sunlight coming from the right side. Again, they're not labeled. That would have been really helpful of the textbook to do. Shade in half of the globe as being like the dark side of the globe, and the other half leave light as the light side of the globe. That will help a lot. That will help keep everything kind of clear in your mind. Okay, so once you have a dark side and a light side like that, notice the date on which this is supposed to refer to. Every one of these problems are going to be referring to what the configuration of the Earth-Sun geometry is on a particular day. In this case, it says June 21st. This next step, again, it does actually say this in the instructions, is it does say, draw the axis of the Earth. Now, I'm going to tell you that there's going to be three different ways the axis can be on these problems. It's either going to be straight up and down on your plot like this in the red vector right there, or it's going to be tipped 23.5 degrees towards this, like with the North Pole tipped toward the sun, like I have here on this green axis, or like on this blue one here, it's going to be tipped 23.5 degrees away from the sun. The book doesn't actually tell you this, but I'll tell you it's going to be one of those three. Okay, on every problem in this, on this problem one, there's a couple of these globes you draw. It's always going to be one of those three. All right, now I'm going to go ahead and say I'm going to pick this one. I'm going to say that on June 21st, the Earth's axis is tipped with the North Pole tipped away from the sun by 23.5 degrees. Let me put down there just exactly what it says on the screen in black. This is not right. I am not giving you the answer here. I am making a mistake. Okay. This is a perfectly good thing where the Earth's axis is tipped 23.5 degrees with the North Pole tipped away from the sun. That's just not June 21st. Okay? So, you're going to have to figure out the right way to draw this for June 21st. But we're going to pretend, it has a different date there. Okay? I'm going to leave that little caveat up there on the screen, though, about this is not the correct way to do this. Now, again, the instructions, if you read them super carefully, do say, first draw the equator. It should be across the Earth there, and it needs to be perpendicular to the axis of the Earth. That's a hugely important step. If you try to draw the Earth's axis, the equator of the Earth, parallel to like the rays of the sun, your diagram's not going to work. You won't be able to get the information off of it that you need on the other questions. So draw the Earth's axis so that it is perpendicular, draw the equator so that it is perpendicular to the axis of the Earth. And when you get that equator on there like that, see how it goes right from the dark side, goes right across the axis of the Earth and over to the light side. When you get it drawn on there, and again, yours will be different depending on what day of the year you're trying to draw, make yourself a little person on the globe, like the little people that are on the globe in example 2.3, or figure 2.3 or whatever. Your little person should be standing at the equator, and his little feet should be perpendicular to the surface of the Earth. His little head should be, exactly opposite in direction from the center of the Earth. If you draw your little person that way, label him person C, and that's the way your lab manual is expecting him to be drawn. Okay, next it says to draw another latitude line, and I would recommend, it doesn't tell you what order to draw these in, but I would recommend drawing the one 66.5 degrees north next. 66.5 degrees north is a weird number. It happens to be the Arctic Circle. Okay, the Arctic Circle is way far north. You know, make it, you know, up near the pole. You know, it's, you can actually, you know, kind of measure it or eyeball it or whatever. If 0 degrees is the equator and 90 degrees is the pole, get yourself about a third of the way from the pole to the equator and you'll be fine. That'll be good enough. The trick here is to make sure that the latitude line that you draw is parallel to the equator that you drew. The diagram will not work if you don't end up with a Arctic Circle that is parallel to the equator. Also, it needs to still be, like I said before, perpendicular to the axis of the Earth. If you draw it that way, then right there where the Arctic Circle is on the sunny side, draw yourself another little person. Again, this little person's little feet should be perpendicular to the surface of the Earth at that location, and his little head should be exactly the opposite direction of the center of the Earth. He's standing on the surface of the Earth, and if you get that little person drawn in there, label him person A, and that will help make your figure work for the future parts of the problem. Again, the book doesn't tell you what order to draw the latitude lines, but the next one I would recommend is to draw in 30 degrees north. If you draw in 30 degrees north, see, it's a little easy now that you have 0 degrees, the equator, and you have 66 degrees. Well, 30 degrees, make it just someplace basically halfway between 30 and between 0 and 66, and you'll be fine. It'll be accurate enough to make these diagrams work. So sketch in 30 degrees north. Again, it's got to be parallel to your equator, parallel to your Arctic Circle. That's perpendicular to your axis of the Earth. And again, put a little person there. Again, his little feet are perpendicular to the surface of the Earth. His little body is pointing straight towards the axis of the Earth. I'm sorry, the center of the Earth. Make him straight up and down with regard to the surface of the Earth right there and label him B. And finally, do the same thing for 23.5 degrees south. Again, that's a weird number, but that's just the Tropic of Capricorn. No, Tropic of Cancer. Sorry, Tropic of Cancer. And how do you even figure out where 23.5 degrees south is? Well, it's in the southern hemisphere, so it's going to be south of the equator, and just don't make it quite as far from the equator as you made 30 degrees north. Again, as long as it's that accurate, it'll be accurate enough for the purposes of the diagram that you're drawing. Okay, again, then draw a little person there, label him D. He's got to be perpendicular, his little feet are perpendicular to the surface, and his head is straight up and down, you know, pointing away from the center of the Earth, and he'll be fine. And you have basically reproduced figure 2.3. With this figure drawn sufficiently accurately, you have a pretty good chance of getting the right answers in the second part of that problem. I would recommend, again, just having worked with this lab manual for many years, go ahead and sketch a few more rays of the sun coming in parallel from the right side of the page here. They will help, okay? For getting the angles right on the next part of the problem, that will be helpful. Okay, now the problem 1 then says to take and make the bottom part of this figure here. Now, there is an example, 2.4, that is in your book where they've kind of got these 4 people here, person A, B, C, and D, and there's the rays of sunlight hitting their head. Now, the book says to sort of eyeball them or estimate or something like that, but to be honest, that doesn't work very well. If you just estimate them, the problem is you won't have estimated them very accurately, and you won't be able to answer the questions about this problem. So instead, we're going to actually compute them. That just, my experience is that works better. So instead of just sort of eyeballing how high above the sun, above the horizon is the sun at location A, B, C, and D, we're going to actually compute it, because you got to do that later on in the lab manual anyway. So you might as in this lab activity anyway, so let's just do it. To compute the noon sun angle, which I'm just labeling here NSA, it's just, in words, it's just 90 degrees minus the distance between your latitude and the latitude of the solar declination. If you've forgotten that vocabulary term, solar declination, from the book, solar declination is a latitude at which, on any given day, the sun is directly overhead at noon. It's the location that it's moving north and south over the course of the year, and it's just the location where at that spot today, the sun will be directly overhead at noon. You're going to actually be computing this a couple of different ways in this lab activity. For some of the questions, you're going to be using a graph called the analemma. For reading off of that graph, where is the solar declination on any given day. You'll also be using a simple equation to estimate the solar declination. In this particular problem, though, I'm going to give you a hint. On these ones where you're just drawing this globe and these people on the globe, the solar declination is always going to be either 23.5 north, the equator, or 23.5 south. Okay? They're all going to be either the Tropic of Cancer, the Tropic of Capricorn, or the equator. So for these ones where you're drawing the globe, You don't really need to like look it up on your analemma or anything like that. Okay, so if I just look at my diagram here, which of these four people, A, B, C, or D, is the sun directly overhead? Well, it looks like it's person D. Okay? Now, again, I cannot emphasize enough, that is not the correct answer of the solar declination on June 21st. 23.5 degrees south is what appears to be the solar declination at this latitude, but that's not right. But that is right for a different day of the year. Alright, so let's see how we would actually compute the calculations for person B. Alright, just to pick one of them off of the four. Remember, our definition of noon-sun angle is 90 minus the distance between your latitude and the solar declination. We've determined that in this diagram anyway, the solar declination is 23.5 degrees south. So if we're at 30 degrees north, the distance between 30 degrees north and 23.5 south is 53.5 degrees south. So then that noon-sun angle is 90 minus 53.5, which is 36.5 degrees. So for person B, the highest the sun is going to get above the horizon on the day that the Earth is configured like this, with the North Pole is tipped away from the equator, from the sun, the highest the sun is going to get is 36.5 degrees. Now I've drawn a protractor on there. I'm not expecting you to use a protractor or anything like that, but just to kind of eyeball in, pretty accurately, at least, roughly how high above the horizon that is. But you see there's two different angles we could be drawing as 36.5 degrees. Which one should you use? I would recommend using, look up at your globe. For that person who is at location B, see how the sun is it's kind of coming from the south? It's coming from the direction of like where person C is. So I would pick the one of the four arrows that are up there. I mean, of the two ways rather that you could draw that arrow, I would pick the way that is coming from the direction where person C is. It'll just make the diagram a little easier to read because, especially for like locations B, C, and D, see how all the arrows kind of seem to be coming from, they're radiating from a location? That'll help, okay? That'll make it easier for you to notice when you're answering some of the questions, how to make those questions work. Alright, so that kind of walks you through how to do that, which is amazingly just problem 1 in my printing of the textbook. Let me show you one more thing that I want you to be able to do on this lab activity here. There's a page where you're going to be creating some diagrams here showing how the rays of the sun spread out when they hit the ground at different latitudes on different days of the year. And so what I want you to notice right away is this diagram has, see how there's 6 little figures here? The one column is all for locations at 30 degrees north, and the other column is all for locations at 60 degrees north. Again, that's not so clear how they've labeled it there, but use that left column for 30 degrees north and that right column for 60 degrees north. Then each of the 3 rows in this diagram here represent a date. The top row is December 22nd, the second row is March 21st, and the bottom row is June 21st. So if you pay attention to the structure of that diagram, then you notice that there's really only 3 more figures to fill in. They give you 3 of them already. So let's actually try to do the one here for a particular day, namely December 22nd, at a particular latitude, namely 60 degrees north. And what I want you to do is, using the kind of processes that we've done in this lab, you're going to figure out the noon sun angle at that location. And let's say you sketch it in something like this. Now I'm going to give you a hint. Make that vector so that it ends right there in the bottom right corner of the diagram. It's going to make it actually work out better. They don't tell you to do that, but that actually makes it work a little bit better. So again, I'm not necessarily expecting you to have a protractor and get that angle in there exactly right, but do a good job estimating that angle. And you'll have your sun angle in there. Then, when you are drawing this, they want this ray of sunlight, this beam of sunlight, to have some width. Okay, it is a fixed unit, 1 unit wide. Like this is a 1 meter wide beam of sunlight. See how they drew it there, where there's like 2 different rays coming from the sun and hitting the ground, and they drew it as there's some distance apart. They labeled it 1 unit. Then on your diagram there, make that beam of sunlight have that same width as what they did on the other part of the diagram there. Okay? If you make your diagram just as wide as their diagram, your results is going to work out a whole lot better. So then you're going to actually be computing how much area on the ground that 1 unit wide beam of sunlight is warming up. And the calculation that the lab manual wants you to do is that this is 1 over the sine of the sun angle. So whatever you come up with the sun angle, you in your calculator take the sine of that, 1 over the sine of that, and you'll get this factor that's called the beam spreading. And the bigger this number is, the more ground that this one beam of sunlight is warming up. And so the less the ground can warm up, because that same amount of heat is warming up a bigger area. That's the point they're trying to get to here, and you're going to be computing the beam spreading for, I don't know, 3 more locations or something, and then you use that as in combination with the answers that they gave you for the other 3 to answer some questions about the role of beam spreading in determining the seasonal cycle. So that's really all there is to this. This one is a fairly straightforward lab if you follow the directions carefully. Your TAs have been practicing this lab and they know all the tricks. I hope you have a great success, and I look forward to getting a chance to talk to you next week.